Okay, time to get started. So let's see here. We are recording, and before we get back into the math, let me just remind everybody, don't forget about the attendance quiz. The clock's ticking. It disappears and ceases to be available 2 minutes after class starts, right? So currently 11, and it disappears at 11:02. Right? So, per my extensive emails and web page writing on the subject, you not only make sure that you get this attendance quiz code entered correctly, make sure it gives you 1 out of 1, right? Reports that you have it correctly entered. You can try again if you need to. If you accidentally typo, no problem. But 11:02 is the hard deadline. And don't forget to have a system in place to remind you to do the code. It is part of the deal, right? And I'm going to make a big deal out of it for the first few occasions, just because I know it's new. But eventually, I won't be. So anyway, reminder, heads up. Okay, so here's where we were last time. We were talking about polar coordinates, and again, different ways to think about polar coordinates. I mean, geometrically, it kind of looks like this, and that does tell most of the story, I think. But keep in mind, there are some very valuable benefits that we're going to see later from thinking of r and theta as part of this function. There's this function in which r and theta are the inputs, the input variables, and then the usual formula that we've already talked about, giving x and y as functions of r and theta. We're going to make big use of this later on. Okay, all right, so with all of that reminded, we talked about the lack of uniqueness, and we talked about the unfortunate notational ambiguity, right? And so again, easy to clarify. All you got to do is just indicate, when you write an ordered pair, r comma theta equals, now everybody knows what you're talking about. Okay. Picking up there. How do you convert the other way? Well, here's a couple of formulas that are easily confirmed. Now, to be fair, this one on the right does have the nasty problem that when x is 0, it doesn't really make any sense, right? So acknowledged. When x is 0, of course, it's pretty easy to just look at the point. Think about the geometry. You don't really need fancy formulas in that case. Okay, what I do want to warn you against is the usual student urge to solve for r and theta. It's so tempting to want to say, r is the square root of x squared plus y squared. Very tempting. Unfortunately, it's not true. It seems like it ought to be true. I mean, for crying out loud, if r squared is that thing, doesn't that mean r is the square root of that thing? Not necessarily. One thing you guys got to keep in mind, this symbol, when you want to write square roots, and you write down, here, let me just write down, I'm going to cross this out just in a moment. But if I were to write down r equals square root of x squared plus y squared, this, as written, suggests that r must be positive. That's what that symbol means, right? The little square root symbol, that does not mean pick whichever square root works for your momentary purposes. That's not what that means. That symbol means positive. Right? So if you write this down, you're saying r is positive, and it does not have to be positive, so this formula is just not true. It's importantly wrong. Right? And I'm going to show you a nasty little counterexample in a moment. Likewise, it is so tempting let me go ahead and cross this out before I forget. So tempting to want to solve for theta here and say theta is arctan of y over x. Super tempting and wrong, in the sense that it's going to give you wrong answers sometimes, which means it's wrong, right? The arctan, right, only takes certain values. Theta is allowed to be lots of other different values that arctan can never recognize. So again, not true, right? So just resist this urge to solve. There's no need to solve for r and theta. You don't need that at all. Let me just scratch this out more emphatically there. You can totally get done everything you need to get done just by using these equations, and then combine that with just a little bit of geometry. Not that, just a little perspective of your geometry is all it really requires. Okay, so for example, let's think about this point right here. We've got this point -1 comma -1. There it is. No big deal. I claim that this point is going to make the sloppy, now scratched out formulas crash and burn badly. Right? So when you take these values of x and y and plug in to there, and take the positive square root, right, and the standard value of arctan, that will give you these numbers here. Actually, let me. These are wrong. So it's going to give you these values of r and theta, which describe this point right here, which again, wrong. Don't blame me. I didn't do it. Right? I'm just saying. It gives you a wrong answer, straight up. Everybody see that? Okay, so beware. Okay, you can get this is a landmine type situation, as I like to describe them. So, much better way to deal with this is again to just take these blue formulas. Right, you take these values of x and y, plug into these blue formulas. These blue formulas give you a couple of possibilities. It means r could be either of these. Right, when you take a square root of both sides, you got to say plus or minus because, right, that's just how that works. And then likewise, bunch of different possible values for theta there. Theta does not have to be the arctan. Right, bunch of different options, bunch of different possibilities. So once you have that written down, now here enters the geometry. And you just have to think about really just which quadrant are you in. That's really all it boils down to. And so, for example, if we were to say, I like this value of theta, I'm going to choose this value of theta, pi over 4. All right, well, that's cool. Pi over 4 is about like that. And now what does r have to be to keep in mind? We're interested in this point, which is there. So given the value of theta that I've chosen, given that I want to get to this point, what value of r do I need? Well, I need to pick the, wrong color. I need to pick the negative value. And that gets me where I want to be. Everybody good? And then vice versa, the other way it could go, again, perfectly fine and reasonable to say I'm going to choose this value of theta that has you going that way, and in that direction, how far do you have to go to get to that purple point that we want to get to? Well, we're going in the correct direction, so positive. Okay. All right. So anyway, heads up. Again, this is not some sort of obscure, implausible. You'll never see it in your experience. No, this is a downright boring example, right, of a point in the XY plane. And yet, if you're not careful, you get the wrong answers. All you got to do is just be careful, think about the geometry, and there's nothing to it. Right? There's an easy solution to what would have been a dangerous misstatement. Everybody happy with that? Oh. Okay, moving along. A bunch of stuff I'm going to let y'all mostly read. As usual, I have a few comments, but again, we're not going to talk about most of this, but don't forget, y'all do need to read this stuff. Okay, so I'm going to skip the first two examples as highly readable. I do like to talk about this third one. There's a little bit of it's good to think through some of these weirder examples. And so here we have a formula. This example, we're going to look at that. Right there is an equation of polar coordinates, so r is a function of theta. Not that it has to be, but that does tend to be most of the time how things tend to play out. Usually, all exceptions granted, r is a function of theta. So this said, what's the picture? What's this curve look like? Right? How do I draw what you might call the graph, the polar graph of this? Okay, well, here's the way I like to do it. I like to think sort of one quadrant at a time. So let's think about these values of theta between 0 and pi over 2. Keep in mind that means we're going to start in the sort of x-axis direction, and then we're going to start looking at a range of directions that sort of turns a quarter turn like that. There's our 0 to pi over 2. Okay. And with that in mind, keep in mind that's the values of theta. We need to now understand, what does r do? As we look in a range of directions that sort of takes this quarter turn, is r sort of like increasing and decreasing, or what's r doing? All right, well, I think it's very helpful to think now about this, what I'm going to call the argument angle. The confusing part is that is also an angle. That's what we're going to be plugging into the sine function, right? It's tempting to think whatever angle you're looking at, that's the angle that's going to plug into whatever trig function you're looking at. Now, again, it's just not true. You see right here, sine, we're not plugging in theta, we're plugging in 2 theta. So what is the argument of sine doing? The argument of sine is going from 0 to pi. Theta is only going to pi over 2, but the argument is going to pi. And pretty easy to think through what r does as the argument of sine goes from 0 to pi. It goes up and it comes back down. So it starts at 0, it increases, and then it decreases, and it ends at 0. So notice that's kind of what we've got here. So as we're looking in this first direction, we go a distance 0. As we look in increased values of theta directions, it increases. It keeps increasing until it gets kind of halfway through. And then it starts to decrease again. And you can see it kind of does something vaguely like that. What do you think? Everybody see the process there? It's weird because we're kind of accustomed to thinking of the input is this way and then the output is that way, and it's always horizontal inputs and vertical outputs, and that's rectangular coordinates, right? We're highly accustomed. Now the inputs are directions, and then the outputs are, loosely speaking, how far you go in that direction. It's a little weird. You got to get accustomed to it. This is a nice little for example. It does get a little strange when you take it further. And now let's think about what happens as theta goes from pi over 2 to pi. So that means we're looking in these directions. Pi over 2 to pi. Again, that's what theta does. What does 2 theta do? My actual argument that I'm plugging into the sine function, the way in which I'm going to understand what values of sine are we looking at, that goes from pi to 2 pi. For which sine does this move, right? Sine then goes like that. And it's a little strange and confusing that first time, right? But when you get a little ways into there, in other words, when you're looking at a direction like that, you have a negative value of sine of 2 theta. So in this direction, right, as we turn, right, as we're going in that direction, our r needs to be negative. And that gets us, along this line, it gets us to, maybe about there. Same game as theta increases, as our directions do like that, r does like this, all of them going backwards. It traces out sort of a second sort of petal of a sort of 4-leaf clover looking deal here. Everybody good? Now, I think it's a healthy exercise, and I want to encourage you all to do this. Think through the rest of the angles, right? Think through the third quadrant and the fourth quadrant. Just healthy exercise. Make sure you can do that, right? We're going to assume that you're comfortable with all that. These next examples are largely just algebra. It's slightly, I just want to comment on some particular moments. This trick right here is a trick. This is not something that will, of course, obviously you would have chosen to do this. I start with this equation, r equals cosine theta is arbitrary equation I just made up, right? And why did I choose to multiply both sides of the equation by r? And the answer is because then both sides of the equation turn into something that's convenient to rewrite in rectangular coordinates. So it's a trick for your bag of tricks, right? We don't do it because, well, that's how you solve it or something. This is just, it's a clever little move. I didn't think it up. Somebody showed me. Right now I'm showing you. Right? So just add that to your bag of tricks. The other thing I want to point out, this, where did the 1/4 come from? This came from looking at this stuff, looking at these x's, obviously the one term moved to the other side, and doing what's called completing the square. And completing the square is an important and standard piece of algebra that I have been mystified for decades, that has simply become unfashionable in high school algebra courses. And I think that's the weirdest thing in the world. It's a very important little move. Now, how often do you use completing the square? I'm not going to say I use it every day, but it comes up. And when it comes up, it's ultra handy. And I don't know why high schools, by the way, maybe your high school is a counterexample. That'd be cool. I don't know. But I don't know why they've largely decided not to do this anymore. But anyway, they don't very much. So make sure you can do completing the square. If you're not comfortable with completing the square, I'm sure it's all over the internet. Just Google completing the square. There's people falling all over themselves trying to, earn the honor of explaining that to you. So it's out there. Make sure you're good with it. And if you want to talk to me in office hours, also totally fine. Happy to discuss it in office hours. Okay. All right. One other little trick I'll point out while we're here, going the other way, converting from rectangular to polar instead of polar to rectangular. Roughly speaking, all you're going to do is plug in the standard formulas, right? We already know that y is r sine theta. So you see in this step, all I'm doing is plugging that in. The one little quickie trick I wanted to point out is don't necessarily do that too early. Right? Now, I could have plugged in y equals r sine theta up at the very beginning. And it would have worked, and I'd get the right answer, it'd be fine. But I would end up having to do sort of like multiplying out a bunch of more trig. And it's kind of easier if you can see it coming that you're going to have not just individual x's and y's randomly strewn throughout your algebra, but if you're going to have x squared plus y squared show up in your algebra, go ahead and let it show up, and then you get to very quickly and efficiently and conveniently just write that as r squared. So, nice little, again, trick for your bag of tricks. Something to be on the lookout for. How we doing? Everybody's all right? Okay, so cylindrical coordinates. It's another coordinate system. Polar coordinates is sort of an alternative coordinate system in 2 dimensions. Cylindrical coordinates is an alternative coordinate system in 3 dimensions. It has a lot in common with polar coordinates. I do think it's important to make the distinction. It's not the same as polar coordinates. Polar coordinates is 2-dimensional. This is 3-dimensional. This is different. That said, most of the heavy lifting of what's actually happening here is rewriting the x and y in terms of r and theta in the usual way. I mean, it's still, theta is still that same angle. R is still, air quotes, how far you go in that direction. And still the same conversion formulas. Oh my gosh, it's so similar. Right? The converting backwards also similar. The only thing that's new is both of them. Well, now it's 3 dimensions, so now, yes, there is this third coordinate. There is this z coordinate. And conveniently, the rectangular z is the cylindrical z. It's, a lot of people call this polar coordinates in space or polar coordinates in 3 dimensions. I think that's a reasonable terminology. It is, however, easier to just say cylindrical. So I encourage calling it cylindrical coordinates. Everybody good? Okay. All right. So not too much to say there. There are some cool tricks that show up here and there. Easy to point out that when you write down R equals C, you get a cylinder. That's where the name comes from, cylindrical coordinates. Also easy to point out that when you have a rectangular coordinates sphere, you get this lucky break again. And so it's not hard to write the cylindrical equation of a sphere. And this is a sphere centered at the origin. This kind of thing comes up sufficiently often. Probably want to make sure to memorize. At a minimum, memorize that that's the trick that you do to get to this equation. Okay. All right. A little bit of a trickier one. Thinking about this equation right here. This is, I'm not going to say that this comes up super often. The point to this example is not the specifics. The point to this example is the perspective we're going to take on understanding this example. So this is an example of a point of view. Sometimes, fairly often actually, you will find yourself with a cylindrical equation where there's no thetas in the equation. Right? Remember how when we were talking about equations of planes and we observed, hey, when there's no y's in the equation, something cool happens. Right? Well, in cylindrical coordinates, when theta does not show up in the equation, something cool happens. And what happens is, if you just think it through, what does a value of theta mean anyway? Well, a value of theta is basically telling you what I'm going to call a half plane. Technically, it's not just a half plane. Technically, of course, that value of theta, you can have negative r's. It does go over to the other side, but I like to think of it as being kind of a half plane. Because points on the other side you would probably be thinking of in terms of a different value of theta. Not that you would have to, but anyway. So I'm going to be sloppy for convenience on this point, and so don't overinterpret from my sloppy use of the term half plane. Okay, so whenever you fix a value of theta, what you're doing is you're looking at a half plane cross section of your surface, whatever the surface might happen to be. Now, in this case, that's easy to figure out. You know, when I'm looking in this half plane, if I want to understand how is z a function of r, well, that's easy. How is z a function of r? In the half plane where z is vertical and r is horizontal, well, that's pretty easy. It's just a straight line. Right now, again, let's technically recognize that, yes, r can be negative, and if r is negative, z is negative. Fine. So that's what the cross-section looks like in that theta half plane. The beautiful punchline on this is that since there are no thetas in the equation, all of the theta cross-sections, all of these slices, no matter how that sort of green, it's like it's a door that's hinged on the z-axis. No matter how you swing that door around the z-axis, cross-sections all look the same. Because different values of theta don't make any difference because there are no thetas in the equation. So all the cross-sections look exactly like this. And now you can just use your geometric intuition. What happens when you take, let's see here, I guess this would be like, there's kind of, this line. And what happens as that swings sort of around the z-axis? Well, you get a cone like I have drawn here. Everybody buy it? Again, the takeaway here, the big point, is not what the cone looks like, or how to deal with that exact specific equation. This is just an example. The point here is that when there's no thetas in the equation, you have a rotationally symmetric surface, and pick any cross-section you like. Once you understand that, you just rotate it around the z-axis, and there's your answer. So very slick little move there. Okay, make sure to read the rest of this stuff. There's a quick comment here about confusion of variables. R is now a coordinate, so you shouldn't use it as a constant if it's also a coordinate. It's kind of like, if you think about it, when you're doing, when you're in the XY plane in rectangular coordinates, X is a coordinate. Don't use X as like a constant representing some. It would be silly to have X be. I'm going to use X to represent the length of the blah, 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 and we'll call it 5, and now you're going to try to do math in the plane, and X also needs to be a coordinate that's allowed to change. That'd be a problem. Right? So likewise with the R. Okay, spherical coordinates. Another three-dimensional coordinate system. Also has a few things in common with polar coordinates, but not as much. It's definitely more different, and yet it remains that a lot of people like to call this polar coordinates in 3 space. And again, I don't think it's enough alike for that to be a good idea. For one thing, we've already decided to call cylindrical coordinates polar coordinates in 3 dimensions. This is different. You can't use the same terminology to think of 2 different things. Okay, all right, so what is spherical coordinates? It's a set of 3 coordinates we use to describe location, just like any other coordinate system. Here's how it works. Theta, like I've drawn here, is the usual theta. It's the same theta from cylindrical coordinates. So it starts off kind of convenient. Again, sort of a half plane. I like this term hinged hinged on the z-axis. It's like there's hinges, like on a door, like that, and that door swings around like that. So hinged on the z-axis just indicates how that sort of rotates around. Is that cool? Everybody happy? Okay. All right. So that's theta. All right, what is this thing right here? That's the Greek letter phi, by the way. So that defines another angle. It's an angle as measured off of the z-axis. Measured off of the z-axis in what direction? There's lots of different directions.
In direction theta.
Yeah, exactly. I was being rhetorical. Yeah, absolutely. So keep in mind there are many different directions from which you could measure an angle. Phi specifically means angle measured toward the theta half plane. So in this direction, like that. So that's positive values of phi sort of rotate from the positive part of the z-axis. They rotate into toward the theta half. And as usual, we have to worry about, but what if it's negative? Negative just means backwards away from the theta half plane. So one thing I like to point out is, and not technically that you have to do it this way, but the way I'm setting things up here, you kind of have to designate theta before you can really even talk about phi. Right? Because we don't even know which direction does phi go until we've decided what theta is. Okay? So do keep that in mind. All right. Now notice then that between the 2 of them, with theta chosen and then phi subsequently chosen based on theta, that defines a direction. And once you have a direction, then we can play the usual game with a, how far. I'm going to call this rho, which is the same notational choice our book makes. It's also a common choice in a lot of contexts, and I'll have to come back and say more about that in a few minutes. But for the moment, we're just going to call that rho. By the way, it looks like a P. It's not a P. It's very importantly not a P. You can't draw a P. It'd be like, if you have an angle alpha, kind of looks like an A. It's not an A. You can't use A in place. It's a whole separate symbol. So take the moment necessary, and it's seemingly ridiculous, but if you don't have practice, as I didn't when I was in your shoes, if you don't have practice making this symbol, you might want to designate a couple, 3 minutes of sitting there practicing. Are you going to go sort of from the bottom and spiral clockwise? Are you going to start in the middle and spiral outward counterclockwise? How kind of a person are you going to be in terms of how you make the rho symbol? But do make sure not to write a P. It's not the same. Okay. All right, so again, that just tells you how far to go. And again, how far is an awkward terminology because it makes it sound like it's a distance. It's not a distance. It is perfectly allowed to be negative. If rho is negative, you just go the other way. Is that cool? Everybody happy? Yeah.
It seems like our longitude and latitude
coordinates
is a spherical coordinates.
It's very close.
It's flat.
I'm going to talk about that on the very next page. Yeah. That there is a close connection. Absolutely. How we doing? Everybody all right? Okay. All righty. Okay, so with all of that said, what are the conversion formulas? Let's see, I guess I got to squeeze all of this in so it'll all fit on the same. There we go. You can look at this triangle here, which I like to sort of redraw it like this. Oh, yeah, question?
So you're rotating on the positive z-axis. So you're going to get it so that it matches where we got to.
Say it one more time.
So your point that you're getting to
This point up here?
yeah, it needs to match with the bottom point.
I'm not entirely sure I understand the question. So this point up here, this is where we're trying to get to, right? And so we've already decided that we have to swing around, theta's got to be a certain value to make theta define a half plane that actually includes the point that we want, right? And then when it comes to, I need to define a direction that literally gets me to that point. Phi is the angle that says how far toward that theta plane you have to rotate to get to a direction that gives you that point. Is that cool? Yeah. So this down here is just kind of a visual aid. I like to draw this point down, dropping a perpendicular down to the XY plane, just because it does make the connection to the cylindrical coordinate R that we already understand. That's really the only purpose this point serves. Yeah. Okay. So I like to redraw this little triangle. What did I accomplish by redrawing this triangle? Very little. But look at the way we have this orange triangle manifested in this picture up here. We know that this is a right angle, but it doesn't look like a right angle. It looks like an acute angle just because of the way it's drawn. So we have a little bit of a perspective problem there, and it's just, it can be a little bit harder to kind of visualize in 3 dimensions when something is turned a little bit. It's just a little bit more geometrically taxing. Now, if you're perfectly comfortable with thinking about the 3-dimensional geometry, that's cool, it's fine, you don't have to do this. I just kind of like to, just to make the picture just a little easier. And with this settled, one thing you'll notice very quickly is that R, keep in mind that's R, well, it's pretty easy to write down a formula for R in terms of spherical coordinates. It's rho sine phi, boom, trig, right? Easy little trig there. And that said, if R is that, let's not lose sight of the fact we already knew that x and y were already r cosine theta and r sine theta. And so, boom, now we have the x and y coordinates. Just a little bit of trig, and remembering the existing formulas we already had. Everybody happy? Okay. Of course, then you'll also notice z is just the other side of this right triangle and is thus rho cosine phi. So altogether, then here's your formulas. These are your conversion formulas, spherical to rectangular conversion formulas. Now, I have a suggestion on this. There's a temptation to memorize these equations. Certainly, you're going to need to make use of these equations. Memorizing them, not a bad idea. For the record, I, in my life, have never memorized these equations. I've used spherical coordinates a bazillion times. I have never memorized these equations, and let me explain why. Because I don't trust my memory. I just don't. I know I've misremembered things so many times. Oh gosh, if I were to memorize these, I am quite sure that at some point I would get the phis and the thetas backwards, or I would have cosine here and sine there. I know I would screw it up, right? But what I will not screw up is understanding the picture, right? So when I need these formulas right here, every single time, no exceptions, I just think through the trig of this little triangle right here. And I just, you look at I don't even draw the picture of it. It's a pretty simple little triangle there. And I just remember, okay, yeah, R is, okay, that's the one that's rho sine, and then Z is rho cosine, and I already know how to do X and Y. So, for your consideration, now if everybody's different, I'm not trying to make you be like me, right? But I am dead set against memorizing those equations for myself, because again, I know I will mess it up. And by the way, for your purposes, keep in mind, the reason you need spherical coordinates is not so that you can make your way through Math219. You need spherical coordinates so you can make your way through future classes that use Math219 and your future career that will use those classes that use Math219. You don't have a 5-week need to know these formulas. You have a 50-year need to know these formulas. And I propose that anything you memorize rote, you will forget. A question of time. That any concept that you understand will stay with you, I don't want to say forever, but almost, perhaps. So, for your consideration. Okay, moving along. So, again, a couple of easy ones. Here's the equation of a sphere. It converts pretty easily using, if you look at the equation of a sphere, this is an identity between spherical coordinate rho and the rectangular coordinates, and you plug that into the equation of a sphere, and out comes rho equals a constant, always a sphere centered at the origin. Again, thus the name. This is why they call it spherical coordinates. All right. Now, we have a fun exercise. This is a brain bender. This is a good little mathematical weightlifting, I think, to give yourself some practice in thinking about the, let's face it, fairly challenging geometry of 3 dimensions as pertains to spherical coordinates. It is confusing. It is confusing. Right? So what we're going to do is we're going to look at this point here. It's that point right there. And we're going to write down its spherical coordinates. And by the way, there's more than one way to do it. Spherical coordinates not unique, just like polar coordinates are not unique. From a certain point of view, spherical coordinates are even less unique. There's kind of 4 different ways to do it instead of just 2 different ways to do it. So let's play the game, see what happens here. All right, now I'm going to start off by thinking in terms of theta being pi over 3. By the way, make sure you can, there's a little bit of geometry to figuring out what those angles are, and it's just real standard geometry and trig. Make sure you can do that. That said, when I say theta is pi over 3, I'm saying we're going to look at that theta half plane, theta pi over 3. And then what is the corresponding value of phi? Well, I mean, I could rotate that way by pi over 4. That would get me going in the correct direction. I can then do a little bit more geometry and figure out the rho, and that's all fine, right? So theta equals pi over 3, phi equals pi over 4 is a perfectly reasonable set of spherical coordinates and the corresponding value of rho. Perfectly reasonable spherical coordinates. Here's the weird thing. There's another way to do that. With the same theta, there's another way to get to that point. And keep in mind, phi, positive values of phi measure toward your theta half plane. My theta half plane, I've already picked theta, pi over 3. The half plane goes this way. Phi, therefore, positive values of phi rotate this way, which means that negative values of phi go the other way, and I could go down like that and thus point myself in that direction. Is that cool? Now, what is that angle? Different ways to think about this. Now, it is, by the way, I recognize, confusing, right? It's, wait a second, which way does it go? No problem. I totally grant that. So you just have to think correspondingly carefully about this. One way to think of it is that this angle plus this angle clearly adds up to pi. But, hey, wait a minute. No, that's if I view this as positive, and in fact this has to be negative because it's sort of going the wrong way. So you can think of it, think it through that way. Another nice way to think about it is that this is already, we know what that value of phi is, and that just subtracts pi. So I think that's probably the easiest way to do it. Think of, let me switch to this mode. That we already know is pi over 4. And then that says subtract pi. So negative 3 pi over 4 is that value of phi. Is that cool? Everybody happy? All right. Now, having done that, once I pick that value of phi, negative 3 pi over 4, what's rho? Well, we've defined our direction as that direction. How far do I have to go in that direction to get to here? Well, negative. So with this value of theta and this value of phi, rho is going to be negative. Let's see here. Negative 2 square root of 2. Everybody happy? All right, now that's 2 different ways to do it, right? For this theta, we can have the positive phi or we can have the negative phi. But don't forget, we can also, let me just clean up this mess. We can also, let's see here, same point, right? Still looking at this point. I could think about it as not that value of theta, but this value of theta. I can have theta, be an extra half turn around, add that extra pi, right? So 4 pi over 3, I can think of theta as going in that direction like that. And now, again, I have two choices. Phi goes that direction. Now that's the weird thing. One thing that's easy to lose track of, when you have sort of one of these weird values of theta where you've kind of gone sort of the wrong direction. Theta, the positive direction of theta is now that way. Excuse me, the positive direction of phi is now that way. Because phi always goes toward your theta half plane. So that's positive phi, which means to get to the direction I'd kind of like to go, now I have a negative phi. Right, so this phi angle that I have in red is negative pi over 4. Everybody happy with that? It's easy to mess that up. It's exactly the same angle we just got through calling positive pi over 4 when we had the theta plane going the other direction, right? So it is confusing, and you got to keep in mind, phi depends on what choice of theta have you made, right? Here we've got a new choice of theta. We have a new notion of what phi is, so that's why this is now a negative pi over 4, yeah.
Would it mean stick phi like down further?
Yeah, I'm going to get to that. Yeah, totally. That's the fourth example. Right. So I just, because it's a little easier to draw, I was just going to start with phi being positive like that, pointing out that this is a negative pi over 4. And then you're exactly right. The fourth option is to kind of go all the way down like that again. Now that is now a positive value of phi. It's positive 3 pi over 4. That defines this direction, which again is the exact wrong direction, which means negative rho would be negative 2 root 2. Yeah.
Could you go like all the way around and then have a positive?
Yeah, sure. So there's one thing I'm kind of sweeping under the rug is that whatever your angle is, like let's say I go like, so there's my phi is whatever that value is. Yeah, you can always add 2 pi. Anytime you add 2 pi, that's all good.
Till like
Instead of negative pi by 4, you make it like.
Oh, you're talking about like this.
Yeah.
Yeah, you can, and that is what I'm going to call that value plus 2 pi. Yeah, so in some sense, as long as we view the 2 pi as kind of the, of course, right? 2 pi is always a freebie, right? Effectively, you're absolutely right, but it's effectively equivalent to this one that we've already done. Yeah. Yep. So there's, modulo 2 pi. These are the 4 different ways to do it. And now again, there's a lot of sort of like geometric gymnastics there. And it's a good exercise. So I strongly encourage you, think through all 4 of the different points of view we just talked about here, right? And make sure you get really comfortable with why they are what they are, because this kind of stuff, you got to be good at. Yes?
So for all ways you have to get to that one point.
Yeah, these are all different ways to get to the exact. So we're describing this same exact point, with these rectangular coordinates, and there's just bunches of ways to do it in spherical coordinates. Yeah. All right, so this is kind of the non-uniqueness. Good geometric struggle. Okay. Somebody asked about longitude and latitude. Yes, very closely connected. Now I've got the globe here set up in kind of a standard way. So the center of the Earth we're going to put at the origin. The North Pole we're going to put on the z-axis up there like that. Now I still have the question of how is the globe rotated around. Just to relate to longitude and latitude most conveniently, we're going to pick the prime meridian like that. The prime meridian specifically in the direction of the positive part of the x-axis. When you do that, what you notice is that theta is exactly east longitude. That's the picture. Right? So yeah, longitude is theta, with the understanding east longitude. So if you want to talk about west longitude, that would be a negative value of theta. Okay. All right. Now, slight annoyance is that there's phi, but latitude doesn't measure from the North Pole. Latitude measures from the equator. So, okay, they're not the same, right? Phi is not the same as north latitude. The connection, though, is that if you look at how those add up, those always add up to pi over 2. Right, so wherever you are, let's say it this way, as theta increases, your latitude decreases, your north latitude decreases. So they're not the same, but there's an easy relationship. So really easy to convert between spherical angles and map angles, longitude, latitude. All right, so with that in mind, here's a really cool, and by the way, of course, as usual, longitude and latitude define a direction, and don't forget that rho is the, air quotes, distance, but in this case we're going the right direction, so it's literally the distance, and that distance is the radius of the Earth, which is, some value. Okay. All right. So here's a cool application of this, and this is a very real-world application. I mean, no kidding, this is important, right? Airlines have to care about the following, and that is, suppose you have 2 points on the surface of the Earth. Raleigh, Durham, RDU Airport right there. And then, that's, Oslo, whatever. Yeah. How far is that? What's the distance? And it's a nasty problem. It's a very difficult problem because this is not a matter of looking at, how much does your longitude change, and then how much is your latitude change, and then calling this a triangle, because it's not a triangle. Right? So, what are we going to do there? You also can't look at a map and measure with a ruler. Y'all know about the distortion of the Mercator projection, of course. So distances are completely screwed up. Maps lie. In their defense, they're trying to describe a curved thing on a flat thing. It doesn't fit, right? They talk about square peg, round hole, right? Well, curved thing, not curved, not going to contain it. So it is a hard problem. But anyway, so back to how do we compute this distance? I mean, how much gas are we going to burn going from RDU to Oslo? And we want to know what that distance is. So here's the slick move. Longitude and latitudes are right there on the map, easy to read, no problem. Look at the longitudes and latitudes. Use these tricks up here to get the spherical coordinates. Then use the tricks on the previous page to get the rectangular coordinates. And once you know the rectangular coordinates of these two vectors, right, you've got R1 and R2 in rectangular coordinates. Then here's a basic property of dot products. Right? Dot products relate to that central angle. Don't call it theta, by the way. It's not theta. Theta is a spherical coordinate. That's a different angle, totally different angle. I'm going to call it alpha. Right? But basic property of dot products. And once I solve for that alpha, I can plug into here, and the distance that I'm trying to compute is just an arc on the sphere, and arc lengths are computed by angles by multiplying by the radius. So it's a little progression. Don't try to turn this into a single formula. The formula just kind of gets out of hand, but it's a strategy that you can easily take longitudes and latitudes, convert to spherical, convert to rectangular, do the dot product game to find the angle, multiply by the radius.
What is big R?
Big R is the radius of the Earth. I think I wrote that. No, I guess I didn't write that. Yeah, that's the radius of the Earth. Yep. Which is the magnitude of those orange vectors. Because, yeah.
Oh, okay.
Yeah.
Also,
Yeah.
we never use longitudes that are not on the equator. Or
Longitude is defined in terms of, like if you're interested in a point, like this point right here, longitude is defined by saying, go straight south in this case until you get to the equator, and then you measure longitude along the equator like that.
so you project it on the x, y plane.
Do what now?
You project it on the x.
You can think it's sort of equivalent to if you were to project. It just gets you to a point in the center of the Earth, which is just a little weird to think about. But yeah, that would work too. It's the same. It's morally equivalent. Yeah.
Isn't it like there's like smaller longitudes? So we never use them, or
I don't understand. I'm sorry.
like as you go towards the poles, the
Yep.
longitudes get smaller, right?
Those distances get smaller, but the angles don't. The angle's the same.
So
yeah.
longitude is defined in terms of the angle, not.
Yeah. Longitude is is this angle, and so you're right that in some sense, the further you go toward the North Pole, in some sense, the more you're going sort of toward the origin. But that purple angle's not changing. Does that make sense?
Yes.
Yeah. Yes.
So we use the dot product to find the angle in between the two radius.
I'm sorry, I just can't quite. If you could speak up just a little bit.
We use the dot product to find the angle in between, like, our
Yep, that's right. Because if you know these rectangles, if you know the x, y, and z for both of these vectors, dot product is easy formula. And you know that it's magnitude times the cosine of that angle. So yeah, you know these coordinates, you know that radius, you just solve for the angle. Yep. So yeah, you're going to have to deal with arc cosine and stuff like that. Okay, cool trick. Y'all can read this one. It's a pretty straight read. Now an awkwardness. This is very frustrating up until you realize how routine it is. But these conventions that I used when I defined spherical coordinates, we call them rho, phi, and theta. Not everybody uses the same conventions. And, oh gosh, the history on this is debatable. But in many cases, physics classes in particular will not call this rho, they will call it R. Which begs the question, then what do they call this thing that we call R? Can't they kind of try not to talk about that? Right, so I think that's super awkward. Oh my gosh. Even worse, these two angles, they switch. Swear to God. They call this phi, and they call this theta. Oh my gosh, okay, so that's super confusing, right? Now, when I was an undergrad, I did a second major in physics, and so I've taken 1 million physics classes, and I've had to do 1 million calculations with these reversed, right? But then I learned them in a multivariable calculus class where they were defined like this. Okay. By the way, when you reverse these, here's another really awkward heads up. You just got to worry about this. When you reverse these, now theta is this angle like that, which is not the same as the cylindrical theta. Oh my gosh. Okay, so very confusing. Now let me try to tell you why this is all okay. Think about rectangular coordinates. And the standard choice, I suppose, is that's X and that's Y. Right? Well, if you take an econ class, that's not X and Y anymore. Now they're like P and Q. Was it P and Q? Or something like that, depending on what you're talking about. And some other context, if you're in an engineering context and You're looking at a relationship between other variables that aren't called X and Y. They're called other things. Maybe they're called L and Q. Well, now you've got a different set of... So the point is, when you're doing rectangular coordinates, I mean, you can't be married to this idea that that's X and that that's Y. You've got to interpret appropriate to the context, and y'all are all accustomed to this. Right? You just gotta, I mean, you gotta keep in mind variables are defined in a context and pay attention to your context. Fun enough. So really this isn't that different. Right? And yeah, it's a little confusing. Right? But heads up. Right? But, always look for clarity on what is the convention being used in whatever context you're looking at. And then just, remember that and sort of get on board with that context, which, by the way, is another advantage to my never having memorized these equations. Because then I don't have to worry about, oh God, did I memorize the physics convention or did I memorize the multivariable calculus convention? No such concerns. I haven't memorized anything. I draw the picture, I interpret the angles appropriately, and I derive my formulas, and they always show up exactly in the form I need them in. Right? Whatever that's worth. So heads up. Right? Now, there are some rules that we have to talk about in relation to this, and so in particular in Math219, conveniently, it seems that Kali always uses the same convention that I've presented, and that's nice. Okay. Related question: if the question that you're working on has established a convention, you have to stick to their convention. You can't say, "Oh, the question uses the phis and thetas in the way that I don't like, so I'm going to switch them." No, unacceptable. You simply can't do that. You'd create this horrible potential for misunderstanding with everything you do subsequently. Anyone who's looking at your work, no one would have the slightest idea what you're talking about. You cannot do that. Does that make sense to everybody? So, and by the way, there are those sometimes who teach this class who, in fact, do not use this convention, right? Because they have a background in physics, or they just decided very reasonably, by the way, that look, the world has adopted a different convention, and so we kind of have to get on board with that convention. So, reasonable point of view that they would do it the other way. And if that's the question you're working on, then you have to stick with that convention. Okay. Last point. If where you're working, for whatever reason, if there is no established convention in the statement of the question or in whatever context you're looking at, you get to choose, right? But you have to be clear what your choice is, right? So you can't just kind of start writing stuff down and not know what you meant and hope that the grader will always interpret it in your favor. That's again not a reasonable means of communication, right? So you've got to make your convention clear. So this is a reasonable way to do it. If you just write down spherical rho comma phi comma theta, well, now I know unambiguously that you're going to use rho for the kind of distance thing, not r. And I can see that you're going to use for the vertical angle, for that angle like that, you're going to use phi. This is a different example down here, of course. And that for your horizontal angle, sometimes called the azimuth, you're going to use theta, right? So perfectly clear, no ambiguity, and that's all you got to write down. And by the way, I do think that it is pretty standard. I think pretty much everyone agrees that you always put the variables in that order, just to avoid the confusion. So using this convention, Kali uses rho phi theta. Physicists use r theta phi. All right, so if you want to do it the physics way, then another way that you can communicate what you're doing, well, you could just, translate this appropriately, right? But you can also write down, if you were to write down this, boom, ambiguity removed, right? No longer, now I know exactly what you mean. If you write this down, well, perfectly obvious that, look at the role that these angles are playing. That's what the geometry is that's implied by these equations. No problem. Okay. All right. Enough of that. Okay, so standard basis vectors. I know y'all remember standard basis vectors. We've done several things with them already. Super duper important in understanding the relationship between linear transformations and matrices, right? Big role that they play in that relationship. A lot of people like to call them IJK. That's fine, but again, if you have more than 3 dimensions, which again, not rare. Not at all rare to have more than 3 variables you got to keep track of. I think it's a bad choice, and E1, E2, E3 so easily extends E45, E6, E7. Okay, so anyway, notational options there. They're nice in various ways. They are intrinsically rectangular, though. Right? Now, in particular, they point in the direction that a single coordinate is increasing. So this vector here, how would I describe that vector geometrically? Well, this points in the direction where x is increasing and y and z are constant. So you can do that same thing for other coordinates. So for example, from this point here, if I were thinking in polar coordinates, well, that's the direction